at the university. I'm Johannes Tschernitz, and I'm a PhD student at the University of Graz. I'm working with Philippe, and yeah, I'm going to tell you a little bit about different I/O formats with pencil code. Yeah, so a bit of an overview what I'm going to tell you. At first, I will compare the different I/O modules, talk a bit of the strengths and weaknesses. So then I will tell you how to select the different I/O modules. Then we can look into how the output looks like when it is generated, and finally a bit about how we can use IDL to read the output. So yeah, there are, in the lecture, I will keep it quite short and just give an overview so that you know how to use it. So there are basically 5 different I/O modules: the I/O dist, the I/O HDF5, the I/O collect XY, and I/O MPI2. So basically, there are differences in how the data is organized. Also, writing speed and storage size can be different for the different modules. So basically, I/O dist is a distributed scheme where in multiprocessor runs, every processor writes its own data to a separate file. And while in I/O HDF5, I/O collect, and I/O MPI2, the data is written to the same file. And I/O collect XY is a bit in between. So there are the leading processors of each XY plane write separate files. In short time, I will going to show you how it looks like in the directory. So the parameters are for the output. They are controlled in the run.int file, and the output scheme itself is selected in the makefile.local. Yeah. Okay. Here we have a schematics how the data is stored in the different files. So in the I/O dist module, each processor writes its own data to a file. So with a large number of processors, you get a large number of files, and this can be problematic when the when the number of processes gets very large, as the file system may not be able to handle that many I/O access at the same time. So if there are 10,000 processors writing 10,000 files at the same time, you can run into trouble. Basically, here in the graphics, the light blue areas are the cells, the data points of the processor. The green ones are the ghost cells at the boundary, and the red in red are the ghost cells of each processor marked. Here we can see that each processor writes also all of its own ghost cells. So data is doubled with the I/O dist scheme. This leads to more storage being used than strictly necessary. On the other hand, the I/O dist module is quite fast in writing terms. So there is bit of a trade-off between storage size and writing speed. And I/O collect and MPI2 and HDF5, we can the ghost cells between the processes are not written, and this has the advantage to decrease the the storage space. But yeah, how the files are written is a bit different. In the IO collect module, all data is collected to one processor, and this processor writes then out the output files, which is a rather slow process. So here we have a large trade-off with writing speed. The MPI2 library is the MPI2 module is quite old, so I would not recommend it for use. And in the HDF5 files, the data is written from each processor to the same file. The method in between, the IO collect, here is it is in between, especially in between in storage size, as the some of the ghost cells are also saved, which would not be strictly necessary. Yeah. So if you want to use the HDF5 module, you would also need an additional library, the libhdf5 OpenMPI-Dev. It's available for Ubuntu systems. I'm not working with Mac systems, so I don't know how to do it there. So, and the one disadvantage of HDF5 is that you need some program to view the data. There is the HDF view, which is a graphical tool, or the H5 tools, which is a command line based interface. Of course, you have to load the HDF5 module on a supercomputer, but this is generally installed by the operators of the supercomputer. Yeah, here, if you want to use the HDF5 or any other module instead of the IO dist, you have to change it in the makefile. So yeah, I can show you how it looks like in the directory. So here I will use the Corona sample delivered with pencil code.
Johannes, can you make the script or the thing bigger, the screen? The writing or the font size or something on the terminal?
Okay. Yeah, you can make the terminal a little bit smaller, and when you share only the window of the terminal, then it becomes larger for the other people.
Okay, I just use here the.
That's good. Yes.
Okay, so here we have the Corona module with empty data directory. So I can use. So at first, I will show you the run.in file. Here, the parameters which are used to control the output are in the run pass. So so here we have the isave parameter, which says which gives after how many time steps var.dat file temporary is written. The var.dat files are temporary snapshots which are used to start, which can be used to restart a run from the certain time point if the run crashes, for example, or the time allocated for the job on a supercomputer is run out, then it will restart from the var.dat. And here, this is the number 50 means that every 50 time steps, every 50 iterations, the var.dat file is written out. Then we can, here it is important to note that the iSave parameter has to be given in time steps, and the time should be selected, so the number of time steps should be selected that about 1 to 3 hours is snapshot is written, so you do not lose the you do not lose so much time if a run crashes, but also slow your run down by just writing permanently data to a disk, which would be also not good if you do not need to write every time the data. So the next important parameter is the dsnap parameter. Here, the dsnap parameter is in time units, so in pencil units, so that here with a 1.0, every one pencil time unit, the permanent snapshot will be written. So you have to, so you can follow the time evolution of your run. So of course, yeah, the IZ2, there are some, the IZ2 parameter is if you want to write a slice, and so, and the dvid parameter governs when a slice is written. So here, yeah, the parameters are also described in the pencil code manual. So it's always good to look them up there. So yeah. Okay. In the makefile.local, we can set the different I/O modules here. Okay, here is what the sample makefile looks like per default. So in a normal makefile, you only only have one line with I/O, and then equals to the respective I/O modules, which says the compiler which of the I/O modules it should use. So I can now run the sample, and then we can, when the sample is run, we can then look at how the output looks like. So this will take only a short time. Okay, it's finished. So, and we can look into the data directory. So here we see now the different files written by the output. So we have here the directories, for one directory for each processor. The sample uses a total of 4 processors, and the data is then stored in the directories for the processors. We can look into the processor 0, and we see here the different files. So here the slice files are the files with the data for the slices, which can be set for what you want to put out. And here's the important files are the var0 and the var.dat. Here the var0 are the permanent snapshots written every time in a time interval you choose in the in the run.in, and the var.dat is also written also at the end. So the end state is written in var.dat. Here, so the run was only for a short amount of time, so we have only var0, the initial condition. But if the run would go longer, there would be then var1, var2, up to, I don't know, any number. Yeah. Also here, in the proc0 directory, the var0 file only and the var.dat file contains only the data of processor 0, and for processors 1, 2, and 3, you find it in the respective directories. Also, other additional output is given, so the params, param.nml and param2.nml are the parameters set by the start.in and run.in files. For example, the dim.dat file gives you the dimension of your setup, so it's then used for reading. Also, in the alt procs are the information about the grid, and yeah, we have also the proc bounds, which tells where the boundaries of each processors are. So yeah, we can maybe, I will change it now. I will change it now to the HDF5, so we IO scheme and have it rerun, so we can see what the changes are. So and because we changed something in the makefile, we have to recompile the code. So this will, while the code recompiles, I will go. I will tell you at first how the output is then organized within pencil code. So basically, the output is separate. The output code is separated from the pencil code. So we have the pencil code routines, wsnap, wgrid, and so on, which then call the respective IO modules, where we have the output snap, output grid, and so on, which then call the IO code from the IO modules or the IO functions from Fortran for the distribute. Also, so, and when we have the functions output snap and output grid are also, for example, in the IO HDF5 module, but of course they are different, so that they call the necessary. So for the HDF5 module, it calls the HDF5 parallel IO module, where are the functions contained to directly use the HDF5 library. Okay, yeah, of course, the IO out with HDF5 could be improved in future iterations of the pencil code with, for example, compression, or we have maybe there will be an HDF5.6 format in the future, but yeah, that time will tell what happens here. Okay, maybe we can. So, okay, the code still compiles. Okay, then. So we'll just talk a bit about how we can read the snapshots. So, for example, in IDL, there is a large number of different routines which can be used to read the snapshots. The routines are written in a way that they automatically detect which output scheme was used and adapt accordingly. So you don't need to have to set, for example, HDF5 manually. So the ones I would recommend if you want to read a full snapshot is the PC read raw, which then can be used to read the whole file. And when we use the PC with the PC get quantity, we can then extract from the array returned by PC read var. Can get the different quantities out. So the routines are found in the pencil code directory in the directory IDL, and here in the we will make it a bit larger so you can see. No, that's not the right here. That's so here in the directory read you can find the necessary routines, which are then written in as IDL scripts. So we can, and they contain good documentaries. So if you want to know how to use it, there is the document piece. So example for the PC get quantity, which is not in the read directory, but in the IDL directory. Here we can have a good documentation. So there are examples how to call the functions on different versions, and here is a list of some of the quantities. And if you want to know all of the quantities which are available via PC get quantity, you would look through the code to get the full list. So
could you also show the header of PC read raw so that we see examples there?
Yes, okay. Okay, here we see the header of the PC read raw. So here the calling sequence, which keywords.
And then below there's a list of examples how to use it. Yeah, just in the header here. Up.
Oh, here. Here.
So if people are wondering how to use the routine, then you see it from here.
Yeah. So the var file by default, it reads the var.dat, but if you, with the keyword var file, you can give any var file you want to read. And the data is returned via the object keyword and tags. And the tags keyword tells you the object keyword returns an array, a multidimensional array with the last dimension, the different quantities, and tags says which index of is which quantity. But I will show you this shortly. So, okay, meanwhile the code is compiled with HDF5, and we can run it again. So let's look first into the data directory. Here we can see that there are no directories for the different processors, and all data is contained in the directory outprocs. Here we have the var0.h5 and the var.h5 files, which now contains the data we want to we got out from our run. So I can now start IDL and maybe I will read the var file. So, and we can now see that in the var file, in the array var, there we have the data contained. Here the corona sample is only a 64 by 64 grid, and here we have 70 entries, so that it returns also the ghost cells. There are so is there? No, there is no.
Yeah, you could also show the tags structure once. Maybe.
Yep. So here we have the text structure, and we have here this index is then what you would use here in this position. So if you want to say maybe like TV scale, maybe.
Yeah, and then you can type, for example, tags.az or something.
Okay, that would be the magnetic vector potential. So, but yeah, it's a bit small because we have only 70 grid points. Yeah, and if we want to get the maybe we want if we want to get the magnetic field in that piece, you can use pcget quantity. So yeah, just sorry, I have to just looking up the so and we can scale Z. So here, let's take no. So and here we see then we get the magnetic field. So yeah, okay, yeah, so that's basically what I wanted to show you. So are there any questions or?
Maybe first one more comment. So if people want to learn more about this PC get quantity thing, that will be another lecture from Vatika next week.
Hi. So I got a question, if that's okay.
Yep.
Okay. So so I was wondering about some visualization tools like ParaView. Is it easy to read HD5 in ParaView as it's currently implemented?
I'm not familiar with ParaView, so I think it.
I can comment on that. ParaView is a bit a special case because they use this VTK format, right? And the VTK requires you can read HDF5, but it requires a kind of
like a header file,
additional tool, right? Or a header file or an interface file that tells ParaView what quantity is what. And that is a bit unfortunate for ParaView because in principle, HDF5 is a general format. Any program can read it. But especially for ParaView, they require that there is an interface defined and you have to actually have it in the code of ParaView. So you would have to change ParaView in order to read pencil files. That is a bit strange to me. But on the other hand, we do have a tool to create a VTK file that is recognized by ParaView from within the IDL routines. So we do have a PC underscore, don't remember, underscore VTK. So you can look it up. It is somewhere in the IDL directory. So we are able to write VTK files.
Okay, thanks.
More questions?